But what happens with the water when you've used it? In going about our everyday lives, we use a lot of water for drinking, washing, cooking, going to the toilet and much more. By using this water, it becomes polluted. The wastewater we produce is known as sewage. Sewage not only comes from our homes, but is also produced by offices, shops, factories and other industries. Together with rainwater that runs off roofs and roads, sewage is washed, flushed or drained into sewers. The underground network of sewers that collect all this wastewater and transports it to the sewage works is known as the sewerage system, and the area it drains is the catchment area. Let's look now at the sewage treatment process. At the sewage treatment works, the incoming waste passes through screens which remove large pieces of debris, such as plastic, paper and cloth. The liquid then flows through a number of channels which take out any grit washed in from roads. The sewage is then passed forward to large tanks. Here, fine particles sink to the bottom and form a sludge, which is regularly removed and further treated. Here we use bacteria to clean up the liquid sewage. The bacteria help purify the liquid by actively feeding on it and turning most of it into carbon dioxide, water and nitrogen. In biological filters, we encourage bacteria to grow in deep beds of irregularly shaped stones. Gaps between the stones circulate air, which lets the bacteria breathe and thrive as the liquid passes through them. An alternative to biological filters is a process called activated sludge, where air is bubbled through the sewage to encourage bacteriological growth. The air can then be pumped or entrained from the surface by rotating paddles. Either way, once the bacteria have done their work, the liquid goes into further settling tanks to remove the remaining particles, leaving clean water to flow to the river or, if necessary, onward to further treatment.
In simplistic terms, nitrogen in various forms is flushed, rinsed, or otherwise introduced into the sewer system. Almost all of this organic nitrogen, urea for example, is immediately hydrolyzed into ammonia. In water, gaseous ammonia, NH3, is almost entirely converted to ionized ammonia, or ammonium, NH4+. Specialized autotrophic bacteria, or nitrifiers, convert the ammonium to nitrite, NO2, and then to nitrate, NO3, through various biological processes. As dissolved oxygen is depleted by the nitrifiers and other organisms in the basin, other specialized heterotrophic bacteria, denitrifiers, are able to thrive by using the oxygen attached to the nitrate molecules for respiration, creating nitrogen gas as a byproduct. The nitrogen gas then simply bubbles out of the water into the atmosphere. Pretty slick, right? Well, let's go back to the beginning and take a closer look at each of these important steps in the nitrogen removal process. First, as a natural reaction in an aqueous solution, or in water, the vast majority of the organic nitrogen immediately hydrolyzes into ammonia. Most of this ammonia automatically converts to the ionic form ammonium. The equilibrium between the gaseous and ionic forms of ammonia is heavily impacted by the pH of the water. A more acidic solution will favor the ionic form ammonium. A more basic will favor the gaseous form ammonia. Since wastewater typically ranges between a pH of 6 and 9, almost all of the ammonia will be in the ionic form. Since ammonia testing accounts for both forms, ionic and gaseous, it is not necessary to worry about each form separately. No bacteria is necessary for this conversion, it just happens. The next step in the process consists of converting ammonium to nitrite and then nitrate. This two-step process is usually lumped into one term, nitrification. This step is facilitated by a specialized autotrophic bacteria. So what does autotrophic mean? There are two broad categories for how organisms obtain carbon required for growth, autotrophs and heterotrophs. Autotrophs are able to obtain their carbon from non-organic sources, such as carbon dioxide and the alkaline bicarbonate. Plants are good examples of how this is done. Heterotrophs, on the other hand, require organic sources of carbon. Essentially, heterotrophs get carbon by consuming other organic compounds, humans and animals being good examples. In contrast to heterotrophic BOD-consuming bacteria, autotrophic nitrifiers require more time to mature and maintain their population in a biological wastewater treatment system. The nitrifiers dictate the SRT in nitrogen-reducing plants. How fast nitrifiers grow depends on the temperature of the wastewater and the amount of dissolved oxygen present. If nitrifiers aren't allowed enough time to thrive, you run the risk of accidentally wasting them out of the system entirely and losing nitrification. Higher temperatures and DO concentrations means faster growth. Colder temperatures and lower DO concentrations means slower growth. Also, when no DO is present, nitrifiers can become completely inactive. As a note, it is important to remember that nitrifiers are also quite sensitive to pH, tending to function most comfortably in water with a pH between 6.8 and 7.5. Once a healthy population of nitrifiers has developed in your system, the first step, performed largely by a group of bugs known as ammonia oxidizers, will take the ammonium and DO and convert it into acid, water, nitrite, and energy. If your system doesn't have adequate alkalinity, the acid produced here could create inhospitably acidic conditions for the bacteria, resulting in major process hiccups including loss of nitrification. The water produced is absorbed in the system, the nitrate moves on to the next step, and the energy is used by the bacteria to grow and multiply. The second step, for which a group of bugs known as nitrite oxidizers is largely responsible, takes that nitrite and more DO and converts it into nitrate and energy. This conversion from ammonia to nitrate is nitrification. Typically, full nitrification is observed when ammonia concentrations are reduced to less than 2 milligrams per liter and nitrite concentrations to less than half a milligram per liter. As mentioned, nitrification is a very oxygen-hungry process. As a comparison, in order to remove 1 pound of BOD, 1.2 pounds of oxygen are required. However, to reduce 1 pound of ammonia to nitrate, 4.6 pounds of oxygen are required. Since getting dissolved oxygen into wastewater is a very energy-intensive process, it would benefit every treatment plant's electrical bill if they didn't aerate more than they needed to. Over-aerating does nothing to improve the process. It really is flushing money down the toilet. After nitrification, the nitrogen is still in the system, mostly as part of the bugs and in the form of nitrate. Though not as toxic as ammonia, nitrates can still contribute to eutrophication and if released into a source supplying drinking water, can endanger human populations, specifically infants, causing what is known as blue baby syndrome, by interfering with blood oxygenation. The final step in completely removing nitrogen from the system is called denitrification. Since nitrification is converting ammonia to nitrate, one could think that denitrification is simply the reversal of this process. Confusingly, yet fortunately, this is not the case. Denitrification is performed by a specialized heterotrophic bacteria. These guys require some pretty specific conditions to perform this step. First of all, they need some food, or BOD. In order to oxidize that food, they need oxygen. Their easiest and first choice for oxygen is DO. If there is no DO present, however, they look to alternative sources, such as nitrate. These specialists have the ability to strip the oxygen from nitrate molecules to satisfy their needs. This critical environment where DO is not present, yet nitrates are, is referred to as anoxic, and is absolutely required for denitrification. These bugs take the BOD and nitrate to produce energy, base, and nitrogen gas. The base is actually very useful in buffering the acid produced during nitrification. The nitrogen gas then floats in tiny bubbles to the surface and into the atmosphere. Though great in the biological basin, denitrification in a clarifier can result in undesirable floating sludge. There are many alternative strategies for developing anoxic conditions. Some treatment plants are designed to have dedicated anoxic zone volumes in the flowchart, while others strive to develop these anoxic zones within the oxidation ditch or aeration zone by rigidly controlling aeration or by turning off aerators for set periods of time. Additionally, under certain conditions, microanoxic zones can be developed within the bacterial flocks themselves, resulting in what is referred to as simultaneous nitrification-denitrification. Various levels of denitrification may be required depending on the local discharge permit. However, full biological denitrification typically results in only 1 to 3 milligrams of nitrate in the effluent stream.
To meet increasingly stringent standards, the cleaned water is often put through a further filtration process. Sometimes shallow gravel beds are used to filter out any fine particles. Alternatively, beds of reeds can also be used to give a final polish to the cleaned water before it's returned to the environment. This method is particularly useful in rural locations.
Although much of it lies underground, there are places where the sheer scale of our water system emerges, glinting in the sunlight. These are our Great Lakes and reservoirs, over 2,000 of them, capable of holding over 700 billion gallons of water. Boreholes suck water from far beneath the ground. Pumps feed from rivers up and down the nation. And they're all connected by an almost dazingly vast network of pipes, some under the ground, some overground. Laid end to end, they would stretch round the world 10 times. On an average day, this system apparently carries enough water to fill 18 million bathtubs.
This is a very basic overview of the water treatment process. Customers always need water, but rainfall is seasonal and increasingly unpredictable. So we often use storage reservoirs to make sure there's always a supply for treatment. By passing water through mesh screens, we remove sticks, water weeds and other large foreign objects. The air takes some odours and gas from the water and allows some dissolved metal salts to separate to be filtered out. We add air by cascading the water down a tower, spraying it into the air or bubbling air through it. At this stage, there are still some fine pieces of matter suspended in the water, along with colour and bacteria. We add a precisely controlled amount of a coagulant like ferric or aluminium sulfate. This reacts with the material in water, making it all stick together to form what's known as flock. To make this flocculation happen, water and the coagulant have to be mixed together very quickly and thoroughly in a special device called a flash mixer. Next comes the clarification process. The flock forms itself into sludge and is separated in a specially designed tank called a clarifier. This sludge layer is called the sludge blanket. To control the blanket, sludge is periodically drained off, concentrated and removed for safe disposal. Particles filtered out on the RGF, the rapid gravity filter, are removed by backwashing. The water now needs filtration to get rid of any remaining particles. Water is filtered slowly through very fine sand or sand-like material. For some river waters, we use ozone gas injection as a treatment stage. This can work in conjunction with GAC or granular activated carbon treatment, where the water is filtered through carbon granules to take out any undesirable traces of largely natural organic materials. The carbon in these filters is removed and regenerated by heat, so it can be used again. Now the water's filtered and thoroughly cleaned, it's disinfected to make sure no harmful bacteria remain. A small, controlled amount of chlorine is the most effective method and provides essential customer protection. This method is used across most of the world. The chlorine has to stay in contact with the water for a period of time for effective disinfection. Last but not least, adjustments are made to the pH levels of the water during the treatment process so that it's neither too acid or alkaline. This helps pipework, fittings and the water itself. From the treatment works, water is fed into a huge mains pipe network, nearly 43,000 kilometres long, which forms a grid around the region. This grid is then accessed directly to your home, and when you turn your tap on, it's available to you. Clean, safe drinking water.